Good morning, everybody. Welcome back to the Dome from Home at the Sternberg Museum of Natural History. I'm Reese, and I'm the director, and I'm here this morning in our Exploring Earth Sciences Hall, and I thought we'd go through an exhibit today and talk a little bit about changes in sea level, because as we talk about all the time, Kansas was once underneath a seaway. Well, a number of times has been underneath a seaway. It's probably spent most of its history underneath the sea at some point in time, which is why there's so much oil underneath Kansas. But what we're talking about now is being under the ocean in the Cretaceous during most of dinosaur time. And one of the things that's cool is you can look at the rocks when you're driving through Kansas, and through different parts of Kansas you see sandstones and shales and limestones and chalks. And these rocks and the fossils that are in them tell us a really cool history about the history of the Seaway and Kansas being covered up by the oceans. Oh, there's Ian showed up. How we doing, Ian?
Good. Great.
So we're talking about sea level history here.
Sea level
today.
history. Oh, I like sea level history. That is something I know about.
So if I flip the camera around here, we're looking at an exhibit that we have that's called Reading Rocks. And what's kind of cool is we can look at different types of rocks, and they tell us about how high the sea level was. And there's in western Kansas, or all of Kansas really, there's a few different types of rocks. And the rocks tell us exactly what the environment was that they were formed in. So if we look, this is kind of cool. There's a little map of Kansas, and you see all these funky little wavy colors, and each of these colors are talking about the ages of different rocks, and you can see that that's the state of Kansas. All right, and down here you see a cool little map where the green is landmass and the lighter turquoise is ocean, and that was sort of North America, the big extent of the Seaway. So what's interesting is we have different formations, and a formation is a type of rock that is laterally extensive and is the same sort of type of rock. And if you go back to the middle of the Cretaceous, or the beginning of the late Cretaceous, as we like to say, about 108 to 98 million years ago, there was a formation called the Cheyenne Formation. And the Cheyenne Formation is made out of sandstone. And sand, grains of sand basically make a trip from the mountains to the ocean. And when you get really sort of mostly pure sandstone, it means you've made it to a beach or out into the ocean. Sometimes you have sandstones that might be river sandstones or estuaries as they go in and get close to a seaway, like you might find where the Mississippi is running into the Gulf of Mexico. So we have a formation of sandstone that's about 108 million years old, and it represents a near-shore ocean environment. All right, so it's maybe even an estuary as we're filling up just the beginnings of a seaway here in Kansas. The seaway's been moving up through Texas and Oklahoma and Alabama, and it's getting up to Kansas. So we're finally getting oceans starting to cover Kansas. As time goes on, we get this period of time where we have a formation called the Kiowa. And the Kiowa Formation is made out of shale. Shale is basically mud. So you get mudstones that get compressed into shales, and what happens is mud doesn't sink out of a water column very fast. So if you were to throw a bunch of mud and sand into a bathtub, the sand sinks out first because it's heavier, and the mud will settle on top. So mudstones mean you're starting to move out, or shales mean you're moving out into slightly deeper water. So the ocean basin's filling up, which means sea level is rising.
So if you think about the way that the Seaway formed, like Reese said, there was one arm that came up, through up where the Gulf of Mexico is now, that spread over Texas, and then up to Kansas, over Oklahoma, and then up to Kansas. And then there was another arm that was coming down from the north. And so what was happening during the Cheyenne, cycle, is that's what's going on, is you've got these two arms that are starting to meet. And then they've just met during the Kiowa cycle, if you will. And then, this is what's really cool to me, is you get to the next cycle, to the Dakota, and what happened is there was a fluctuation. So those arms actually pulled back again, and the sea got shallower, and it wasn't a continuous seaway. And there was a little bit of deepening and then shallowing, and it was very, what's the word I want? Fluid. Very fluid. It was not very static, I guess. So that's where we are in the history of the Seaway at this snapshot.
So with the Dakota sandstone, things are getting shallower, as Ian said. So sea level is dropping, and it's dropping enough that some of these sandstones are actually more river sandstones or estuaries. So we can see that because the sea level is dropping, we got this influx of forests. So we've got trees along these rivers that are basically along where the coastline is moving away as sea level drops. So this is a time period when we get leaves. We got tons of fossil leaves, and the first leaves, even found by George Sternberg, come from the Dakota sandstone. So sea level was rising to get to the Kiowa Shale, and then now it's dropping, and the sea level is moving south and north and leaving a little more exposure in Kansas. But then sea level starts to rise again.
So this is where it gets exciting, because you got your two arms that were sort of pulling apart. Now the two arms of that seaway from north to south connect again, and they stay continuous for a very, very long time from this point on out. Now, that doesn't mean it doesn't get shallower and narrower, but it stays a continuous seaway from this point on.
So now we're at around 92 million years old, and we have a shale called the Graneros, right? So we know that sea level is getting deeper because we're back to muds again. We don't have the sand as much for sandstones, but we have a muddier seaway, and we start getting a few sorts of interesting marine invertebrates. We've got this is a part of a shale that's got impressions or molds and casts of clams. All right, so now we know, as Ian said, the seaway is completely connected, but it's also now going to get deeper. And so as the ocean gets a little deeper and deeper, we start getting a rock type called limestone. And limestones suggest deeper waters because now we're not having so much shale. The shale's a little bit closer to the shore, and once the shale deposits out, we have the ability for limestone to take over, which means there's always lime in the ocean, but it gets overwhelmed by sandstone and shale.
Put the lime in the coconut and shake it all around.
So once we're deep enough water that means we're far enough away from the shores, we start getting limestone deposition.
So you mean it's not that kind of lime? It's not the citrus lime that we're talking about?
It's not our citrus trees, although it would be nice.
It would be. It would be refreshing.
So now we're in what's called the Greenhorn Limestone. That is the formation. And now we start seeing all kinds of marine critters, right? So we've got, here we have some casts of a variety of clams, inoceremus shells, worm burrows. We've got start seeing some ammonites. show up in the fossil record. We get all kinds of marine invertebrates. And there's also some marine vertebrates that show up. And the Greenhorn is where we get the fence post limestone, which is sort of famous limestone that was used to make fence posts back when there wasn't a lot of trees for a lot of the pioneers to set up their fences for their livestock.
Fence posts, among other things. I mean, they made buildings too.
They made buildings too. So once we get this high point of sea level, then interestingly enough, it drops again in a cycle of rising and falling sea level. Sea level drops again, which means, take a guess. What comes after? If we're going back down from sea level dropping, means we're getting closer to the shore, which means now we're going to start getting shales again, right? So as sea level drops, it means that the sea line or the seashore is getting closer to where we are, so we get more shales, mudstones. But we're still in the Seaway, so we still have all kinds of cool marine invertebrates. So there's a neat ammonite. We do get our clams. We get all kinds of really cool ammonites. Ammonites, what are ammonites, Ian?
Ammonites are invertebrates. They're cephalopods. They're related to squid and octopus. They've got tentacles, just like a squid or an octopus would, but they have a shell that sort of protects them, and they are related to the extant nautiloids that we see in the Seaway today, or in the sea today.
And this is also a time where we start getting some snails. We get gastropods, and we also find we start getting crabs. We get crabs. We have arthropods. We get barnacles. So it's a fully marine, fun, interesting, but shallower seaway because we're getting all these shales.
It always amazes me that people can interpret a worm burrow, because I miss that. I just see weird lines. It always amazes me that ichnologists can look at that and go, oh yeah, that's a worm burrow. A little squishy critter created those burrows. It never ceases to amaze me.
Ian brings up a fun point, because what's really cool is you can tell a lot about the energy, like whether you're in a wave zone or whether you're in deeper water, by what types of burrows you find and how mixed the sediment are. You can tell if there's lots of oxygen, because sometimes you won't see any burrows because the sediment gets mixed up so much, because there's so many worms and things just chewing up and mixing up the seafloor. And if you have lower oxygen environments, you find a few little burrows individually. You can trace distinct burrows around because there wasn't enough oxygen for them to be tons of animals. So you can do all kinds of cool stuff with trace fossils, right? Which is really quite awesome. Like I said, if you have lots of high energy, all of your burrows are very vertical. They go straight down, straight up and down. And if you have light, if you're in a fairly quiet environment, they can cruise around horizontally a lot. And they may go down a little bit vertically and then spread out horizontally, because there's not enough energy to uncover their burrows. Well, with that cool sidetrack, we see that the Seaway, the sea level goes up again. And if the sea level goes up, then that means the shale is being trapped closer to the shoreline, and we're ostensibly getting deeper, right? So sea level rise, we now end up by 87 million years ago into what we call the Niobrara. And the Niobrara has chalk formations. So we're deeper water now, and in this deeper water, we get some really gigantic, huge inoceramid clams, which are quite amazing. And they're they're almost like dinner tables, but they're large, relatively flat. And because they're in chalks are pretty soft, squishy areas. And so these things do what we like to call snowshoeing. They don't want to sink into the chalk too far because they got to get water to go siphon through so that they can collect food. So they have these big flat shells to sort of stay at the surface. And because it's such kind of soft, squishy ground, there's not a lot of room for, there's not a lot of other invertebrates that are around that don't need a place that's relatively hard to sit and survive on. So these large inoceramid shells have all kinds of cool smaller shells of oysters and different sorts of clams that attach to the big inoceramid shells so that they have a hard ground, they have a place secure to attach to so that they won't get buried or sink rapidly into the chalk. So they have a place to live. So they become their own little communities in these environments, which is really pretty impressive. So you find one complete big inoceramid shell, and you will find a whole community of other mollusks that lived with and on top of them, which is kind of awesome. We also have, in this area, a cool kind of bivalve that do a different sort of thing. They're called rudist bivalves, and this is a type called Durania. And it's weird because it's hard to tell that they're a clam, but these particular ones lived sort of communally. Each of these little holes in what looks like a honeycomb is an individual clam shell, and they grew in these colonies. So their shells actually cemented together, and each individual shell looked like sort of a whole individual long tube column, and then each one of these had a little flat top shell. So there were clams that didn't have shells that were symmetrical, which is really weird, and that's why they're very rude, as rudest bivalves. Very rude of them. But these guys would live, and they could grow up, and as they got bigger, they might sink into the chalk some, but they always kept the top of them at the surface, where they could open up flip their lids, and be able to circulate water and filter feed. And once we get to the chalks, we get all kinds. That's where we get all kinds of marine vertebrates. We get lots of sharks and mosasaurs and all sorts of things. Lots of fish. And we also get some squid, which is kind of cool.
Squid.
That's a big squid. So everything is bigger. So the rudists are bigger, the inoceramids are bigger, the squids are bigger.
So what is that? How do we know that's a squid? I thought squids didn't have hard parts.
Yeah, what is that part?
What is that part?
This is the internal skeleton of a squid. What's it called? It's called a pen.
Pen.
A squid pen.
For some reason I was thinking radula, but that's not right.
Nope.
That's more
That's the rasping thing, yep. So we still have ammonites. So we have large squid, large ammonites, large sharks, large fish, large mosasaurs. Everything gets bigger and scarier in the Niobrara Formation. And after we get to this deepest part of the ocean, or of the whole Seaway, from 108 million years, now we're into 70 million years, 77 million years, we're at the deepest part of the ocean. And at this point in time, we're starting to get shallower and shallower, and the last formation we have in Kansas is the Pier Shale. So, right, we're going back from our limestone chalks to shales as the sea level drops. And
So this represents sort of the last sort of regression, where it's starting to shallow and narrow and eventually begin to separate again into...
it's the beginning of the end.
It's the beginning of the end.
It's the beginning of the end. So the Seaway is shallowing, and eventually the connection between the Arctic area and the Gulf of Mexico is separated, and Kansas becomes dry, and the Seaway is continue to shallow and move back and regress back to the north, to the Arctic, and back down to the Gulf area. And the middle of the country starts to become terrestrial and dry up to where we have what we look like today. And the forest will start to move back into Kansas, and we will move back into being strictly a forested area, and will remain like that for another 20, 30 million years before we start to get to evolve some grasslands eventually. So we can see that the sea level in Kansas, let's see, basically rose and fell, let's see, 1, 2, 3, at least three major cycles.
And those are just the really, really big ones.
Those are the really big ones. There's much smaller sea level rises and falls on much shorter time scales within each of these bigger cycles. But what caused the sea level to rise and fall? That's the interesting question, because during this whole time, there wasn't an Antarctic ice sheet. There was not an ice sheet in Greenland. So if there was no ice if it was an ice-free world, how in the heck is sea level rising and falling?
Well, was there also a greater amount of volcanism during that time?
There was some volcanism.
Where?
Where was the volcanism?
In space? Not aliens.
Well, we know that North America we'd split off from Europe and Africa, and we were moving west. So we were grinding along and running into an oceanic plate to our west, the Pacific plate, and it was grinding underneath us and doing a lot of mountain building in the Rocky Mountain region. And so we have some sea level that's rising and falling based on the fact that we're lifting mountains up to our west, starting way over in Utah area. And we had a couple of different mountain building episodes. And also, a lot of that would actually help lift things up and have sea level fall regressions.
Right.
And when the mountain building slowed down, we might have some transgressions. And the big thing, worldwide sea level transgressions, happen because, well, we're splitting off as we're moving away from Africa and North America. We have a bunch of hot rocks, sea level volcanism going along in what we call the mid-ocean ridge, the ridge that's basically shoving North America and South America away from Africa and Europe, is a bunch of hot magma moving up and raising up sea level in the middle of these continents.
So kind of a seafloor swell.
So a big seafloor, we call seafloor spreading event. And what that's doing is raising the level of the seafloor. So it's kind of like if you have a little plastic swimming pool, and if you stick your hand underneath the swimming pool and lift it up in the middle of the pool, you're going to flood all the water outside of the swimming pool. So that's kind of what's happening, is sea level basin is rising up and shoving all of the ocean water up over the continents. So it's really rapid, lots of volcanism and rapid plate tectonic movement, rapid seafloor spreading is what's lifting the oceans up onto the continents, with creating sea level rises. And regionally, it's the mountain building that can cause some regressions, or if the seafloor spreading slows down a little bit, then we have the opportunity for rocks to cool and the sea level will drop a little bit. So all these different fluctuations are happening during the Cretaceous that has nothing to do with ice, which is kind of fascinating, because we always think of sea level change being correlated to the spread of Arctic and Antarctic ice sheets.
Ice baby.
Thank you. Thanks a lot, Vanilla. So anyway, that's just a little history of seafloor spreading causing rises and falls in sea level that affected Kansas and put us under a seaway and gave us the coolest, most fascinating geologic history and paleontologic history of oceans in Kansas.
So one more thing, useless piece of information that I will add is, if you look at the ocean today, a lot of what drives our ocean is sort of hot and cold, and sort of what we call convection, along with streams. Gulf streams. What do we call that?
Currents.
Currents. Thank you. That thing that the water does. Our seaway was a little bit different. There's a hypothesis that the seaway during the Cretaceous was actually storm-driven. There's a lot of evidence of storm gyres on both coasts, I guess, of the seaway, both shorelines. So you would get storms coming from north to south, really coming down from the north on the on the western margin of the seaway, and then you had storms coming from the south going north on the eastern margin of the seaway. So that's what sort of drove the circulation of the seaway, and that's what caused the mixing of the warm water from the south with what we call the boreal sea, the colder water from the north, as well as a couple of different kinds of freshwater inputs from both the Rocky Mountains as well as the Appalachians. There you go. Now you can impress your friends at the next post-quarantine get-together you have over cocktails and tasty beverages. You can tell your friends, did you know that the interior seaway was actually driven by storms? And they'll go, ooh, your knowledge. You're welcome.
All right. So for Ian, I'm Reese, and we're happy that you joined us for the Dome from Home. As always, please give us a like, give us a share. We always love to have new followers. So if you share it and get a lot of your friends to join us every day, then we appreciate that because we enjoy our time with you.
I want to give a shout out to my friend Mark Wegner. Thank you for watching. I
All right.
appreciate it.
Thank you all and have a great day.